Hi guys, thanks Sumo for welcoming me back to another speaker series. As Steve mentioned, I will be talking about my experience working at startups, as well as going to some of the more technical aspects of what I was actually doing there, which I think is generally of interest to engineers as a whole. A lot of people tend to go, oh, I worked at this company, but you never actually get to hear what people actually did. When Sumo asked me to do this talk, I thought it'd be interesting to talk about startups in general, because I think it's kind of an area of industry and an area of work that people don't get to hear about too much. And so hopefully you find my experiences interesting and educational. So get started. This is just a general summary of what I thought I'd talk about today. First thing is why I became interested in joining startups. As Steve said, I kind of only really worked in startups. I worked at Qantas for a little bit and did not enjoy it very much. And I'll go into some slight detail as to why that is. And then for a lot of people, I think startup kind of just means like Facebook and the social network, and the actual experience of what startups, how they actually evolve and how they work, and the actual process of working in one and building a startup. I thought I'd just give some background to that, and as well as my experience of actually going through that process, because it's pretty different to working anywhere else, I think. The next thing is actually talk about the company that I spent 3 years working for, which is BioScout, what they do, how I got involved, and kind of their process and their journey, where we worked, how we worked, finance, R&D, all that kind of stuff. And then finally, kind of a brief overview of the technical stuff that I actually did. This will be kind of, anyone who's done 1701 or doing 1701, this is kind of going to be like, oh, wow, hey, I actually use system block diagrams. And kind of just a general overview, be like, okay, yeah, sure, you have a product, you have a thing. How do I actually build it? What does it actually look like when you're trying to develop something? So that's kind of the general structure of what I'm talking about. I might go off on some rants at some point, but I will try and get through everything in reasonable time. So firstly, I guess the question is, why would you go work at a startup? There's no money, kind of unstable system. You might get fired, the company might go under, who knows? And I guess this is kind of both the disadvantage and the appeal of actually working at a startup. You're kind of a big cog in a potentially unstable system, which I think a lot of people kind of back away from a little bit. For me, that was actually why I sort of wanted to join. So at the end of second year, I worked at Qantas for a period of like 6 months, doing like software, like your kind of basic software stuff, like backend databases, that sort of stuff, which was fine. It's sort of the like bread and butter of the software industry, but it wasn't particularly interesting. I remember I spent 2 weeks developing some function to do like database query calls. And then when I put it into software review, the guys turned it down because I used a for loop, and apparently that's bad practice. And I was like, come on, like, what is this? This is not interesting. And so I became interested in joining a startup because for me, that was the opposite experience. No one's going to tell you really the way you're doing something is terrible, because at the end, end of the day, that's not their motivation, right? And, working at a startup sounded fun, sounded interesting, bean bags, ping pong tables, it's all good, right? Well, kind of, yes and no. So firstly, when people say startup, and maybe this is more aimed towards the first and second years, I guess, who kind of don't really know what it is from an actual company perspective. I thought I'd just briefly go over what kind of people actually mean by startup. Is it another buzzword? Like a little bit. Basically, a startup is a small company that's trying to build a product. And the main thing about startups is that their product, they're developing like this, their key interest is the product that they're trying to get out. And they don't really have time or the money to sort of do anything else. They're not established. And most of their finances come from seed rounds and incubators, which I'll talk about a little bit in a second. But these are kind of like, in the world of startup, these are sort of like the two key places, particularly at the beginning, people get money from. You don't have a product yet, so you're not selling anything, and you're not making profit on that. You need some other way of keeping you supported, and basically you get people to invest. You get companies to invest, such as incubators or venture capitalists, and then you have the seed rounds, where basically you go out and say, hey, look at me, I'm building this awesome thing. Is there something that you would be interested in investing? And that's kind of what a seed round is. Startups often come out from an attempt to solve a specific problem. This is just in general terms, I guess, rather than as a product. They're a problem first that someone is trying to solve, and they come up with a solution, which more and more recently is something called software as a service. So pretty much most of the companies, the startups nowadays are software as services. And the reason being is because that's really easy to develop. Everyone's got software. You don't need to, you've got companies like Amazon and Atlassian, which provide services for other companies to use the software. And so everyone's trying to come up with like these software solutions nowadays. You've got thousands of companies who are startups that the whole point is to invest in other startups. And these are often venture capitalists in general. You often see people come out and be like, I'm going to get lots of money to then invest more money into other people. At the bottom of the slide, I've got a list of kind of maybe some of the biggest startups. None of these are startups anymore, but they're all originally startups, and they're all there to try and solve some kind of problem. Facebook was, I think everyone's seen the social network. You can make lots of arguments as to what the problems they were trying to solve there. Dropbox as well. Airtree and Atlassian. Atlassian is probably Australia's, if you don't know what Atlassian is, they basically provide software framework for software engineers, which is kind of a pretty niche market to be in, but because there's so much money in software now, they sort of hit the jackpot a little bit. Uber is the other one. So Uber is kind of, everyone knows what Uber is, but originally their problem is slightly different to the other ones, you could argue, because everyone else was trying to solve a key commercial product, whereas Uber was trying to gain the capitalist system basically. And so the problem they were solving was that everyone can be their own business owner. And so that kind of started the whole Uber, Airbnb sort of thing. But these are all the success stories of startups. So one of the other things about startups as well is that when people get investment, you generally these things don't succeed, right? So when you have small ideas, they grow, they become bigger, but most of the time you're not going to succeed. So one of the companies that the world's biggest incubator. So an incubator is a company that, or I don't know if you call it a company, but it's an entity, right, that invests money with the intention of trying to help startups succeed. So whether that be investing, mentoring, and actually helping you develop a business. And the reason why people do this is because the success is amazing if you have a good company. So I'm just looking at some stats here. That's why it's on my phone. I didn't put it in the slide. So Y Combinator, which is the world's biggest startup accelerator program, their acceptance rate is 1.5%. So there might be thousands of companies that apply every year to try and get investment from Y Combinator to grow their business, right? They have 1.5% acceptance rate. Of that 1.5%, 20% fail as companies within the first 6 weeks, right? But 1 in 10 who make it through are worth 40 million after 2 years. Right. So this is why we're kind of in the golden age of startups, because if you succeed, you're making incredible amount of money, right? I guess that poses the question, why do people go into startups? As a founder, or as someone who wants to work there, very high reward, but very high cost of failure, right? Otherwise, if everyone could come up with a new idea, we wouldn't have a Zuckerberg, right? He wouldn't be famous because everyone would be doing it. Everyone would be doing it. So what's the difference between startups and I was talking about before and the startups I worked at, and maybe some of the more interesting startups to us as mechatronics and mechanical and aero engineers as well. As I mentioned before, a lot of startups in general provide a thing called software as a service. It's basically, you hear this term a lot around. It's basically where you have an interface for the user. It might be some software platform, might be an app, which everyone loves nowadays. It might be a website, right? And then the user looks at it and then gets some information back. It might be some graphs, something, but at the end of the day, it's data processing, or all they see is as the front end user. And this is pretty the hardest thing there is the idea and selling it and getting clients, of course, but there's no real problem in the actual development side of things. If you think about it, like Uber is like the simplest app in the world, right? Like how many Ubers that follow the same framework are there? It's like every single food ordering app in the world. It's every single shopping app, basically. They're all sort of the same thing. It's not complicated. It's the idea that's complicated, right? Tech startups are not, or deep tech startups are not at all, because you have this thing called hardware, which, as any slightly older engineer will tell you, is a pain in the ass to deal with, right? Hardware, well, it's difficult. BioScout is a hardware-led startup, and these things can succeed, but you have to add, on top of the selling the product, developing the product, like selling the product, building client relationships, building a company, you also have to develop the actual product. The product isn't off the shelf anymore. It's not software as a service. The thing that you're relying on, and you'll see this becomes a little bit clear when I actually talk about what BioScout does, because I'm sure this is all a little bit just like, okay, this is cool, but can you give us some concrete examples? The interesting thing is, at the end of the day, your product still actually is software as a service, right? Unless you're like Tesla, where your service is a car, right? A lot of the time you might build hardware which provides something, particularly in agri-tech, because you might put robots in farms or things like that. But at the end of the day, they do a thing, and then the information goes to the farmer, and suddenly you're back at square one, but with extra steps. So this is kind of one of the reasons why tech startups are much more difficult, and they also fail much faster, because you can't pull off the shelf solutions. Like they're not there immediately. You have to develop it themselves while doing everything else. So what is BioScout? Let's talk about that. So BioScout is a agri-tech startup, agriculture tech startup. Basically, the problem we're trying to solve is the problem of disease in agriculture, specifically horticulture, which is like avocados, blueberries, bananas, those sorts of things, as opposed to just like kind of your more generic agriculture, which is like wheat and things like that. And basically the problem we're trying to solve is the infection of these plants is hard to detect. And more specifically, once often areas of fields get infected, it's often too late. So usually there's like a 3 or 5 day grace period once they get infected, and then you kind of lose batches and batches and batches of crops. And you waste a lot of money on pesticides, and you also waste a lot of money just on losing crops. So the solution to this is real-time analysis and detection of airborne diseases. That's sort of like my elevator pitch that I've been working on for the last 2 years-ish. It hasn't gotten any better, but that's what it is. And so the general principle, well, so I'll get to that in a sec. The company started, I don't know, maybe 5 years ago, out of the CEO's PhD at UCID. So all of the guys who work there are all engineering backgrounds. Some of the older ones might know them, but they basically, the CEO was in 5th year when I was in 1st year. And they were all kind of around engineering, and they've all got engineering backgrounds. So we have the founders, mechanical engineering, software engineering, and maths, then biomedical engineering and science majoring in immunology, and then biomedical engineering majoring in mechatronics. This is basically the background of the 4 co-founders who started this company. So it's kind of interesting because none of them have backgrounds in finance or business or anything like that. And kind of over the course of the growth of the company, it became pretty clearly, you know, like when people say, oh, a lot of engineers become managers, it's true often in the sense that we have to learn how to be businessmen, but I think sometimes it's harder for businessmen to be engineers because at the end of the day, you can do finance and make rational decisions, but it's been interesting to see the kind of the change. When I first started working there, everyone was like engineering, engineering, engineering. And as time's gone on, people have like taken a little step back to look at things in the same way we look at problems maybe super mathematically or from a design perspective, starting to think about things more from a business side of things. It's just interesting. As engineers, you have to adapt. And as working at a startup, you have to adapt to do multiple roles. And as time goes on, you become less of an engineer and more of a CEO, potentially, at least as a co-founder. One of the things I found while working there was I had the luxury, and also kind of the decision of doing my best to not be involved in any like finance discussions. They'll be like, oh, we're talking about business or like this week's profit. I'll be like, I'm going to be over here writing code, which I think is working startup is a very, particularly such a small one, 4 to 5 employees, is you can kind of go either way. If you're interested in being in finance or learning more about finance or the business side of things, you could go and very easily learn about that. And it's kind of a good thing and a unique experience to being in a startup, because you actually get to see the whole sort of like gamut of roles, from like HR to engineer to, you know, financer to businessman to like manager. And going back to the company, just in terms of the principle, how it works is that we have sensors that go in a field. So you can see here, I am proudly standing by a box, right? And with a big solar panel and a wind vane. And basically we've developed like a research center in a little box, and it goes, and you can see on the right, it goes onto a pole in the middle of a farm, and it detects stuff. Like we're not talking about like software kind of sitting airy-fairy in the cloud. Like this is a thing that we've built and designed. There's some photos later on of like the insides. I couldn't give too many pictures because IP, but basically it's like real engineering, there's tech in there and stuff. And this thing sits in a field and senses stuff. It analyzes stuff using a lot of principles that we learn at uni. And a lot of sensors going on, a lot of data going around. And then that goes up to the cloud. And then the farmers get feedback, which at the end of the day is like a graph or a text message or an email. It doesn't really matter. It's, despite you've got all of this hardware and all this tech in the way, all that lets you do then is then send an email to someone saying, hey, check out this section of crop, which is kind of like a little bit, I was gonna say upsetting, but it's sometimes this is like the reason why it's hard to pitch startups, because you're like, you have all of this middle process and all this really technical detail. And at the end of the day, you just get an email, and it's hard to explain the like kind of significance and importance of that. Oh yeah, I forgot I put this slide in. This is just some stats on what is previously done in this particular industry. So BioScout kind of came in, and the only tech that was doing the same thing was like from the 60s, and they're these huge, basically black boxes, and then you sit there and you put like a sample in, and then they send results off to the lab, and then they come back and you get results in 2 weeks, which is a bit late. They also look at like weather and visual systems, but as I said, if you miss it, you kind of, there's 3 to 5 days before you actually see signs of disease infection, and by then it's kind of too late. And so yeah, this was the problem that they were trying to solve. I got these slides off the guys at work. So I think this was one of the slides that they used to use in their pitch decks. But yeah, there you go. So it's a huge problem, and 20% of crop yield is lost in disease. And Australia is one of the world's biggest crop like exporters. So it's a huge amount of money. It's a huge industry. And being in agri-tech in Australia, because think of like our land mass and how much of it is used for agricultural development. It's a lot of money, and it's a huge problem. So again, just another real brief slide. This is kind of the overview of the system from a, this is what, if you were a businessman pitching, this is how you would describe the system to someone. This is, you'll see later, I have a slide, which is like the engineering way of describing the system. But basically, this is all they get. You have a field sensor, you get text alerts, and analysis dashboard, because you can kind of see in the analysis dashboard, if you put all the all the sensors in the field, you can start actually doing interesting things about like actually mapping like trajectories and projection of diseases. So if you have disease moving through a particular area, you can kind of, and you know the wind speed and certain things like that, you can actually start seeing the movement of it and see if it's going to go to other sections of farms or other parts of the area. So there's a kind of general principle of how you go about things. A little bit more about what we do. So we are all basically the left and the bottom. We're not in wheat so much at the moment. And the kind of interesting thing, and I'll get onto this more in a second when I talk about how the company developed. We were originally looking at wheat rust and powdery mildew, which is in like wheat, basically, and barley and those sorts of grains. That was the original concept for the company when I started working there. So we were going to do the same thing, but in a completely different area of farms. And I'll talk more about that in a sec. But at the moment, we're in horticulture because it's kind of easier and it's also more expensive. So that's just a little background on what we did. I don't know why that slide in there. It's more about if we can help, it's because we reduce these things. No chemicals because we get rid of pesticides, increase crop yield, and farmers happy, right? So how did I actually start working at BioScout? So here's some photos of us. If anyone's a biomedical engineer and has been inside the PhD lab down the bottom of a mechanical engineering building, if you go right to the bottom, there's this tiny little door on the left out the back, and it's where they squish all the PhD biomedical students, right? This is that lab. So when I first started there in 2017, Lewis was the CEO. He's the guy on the right in the far right-hand picture. He was doing his PhD in what has become the company, basically. So I think originally it was on using drones to detect diseases in agriculture. Was the general principle of the PhD, and it turned into a company, and we started working out of this lab because no money, right? No, we couldn't sell anything because we didn't have a product. Remember, it's not software as a service. You have to build the thing to get the data. It's not like you can go web scrape, right? You have to build the thing, and then where are we going to put it? Do we own a farm? No. So there are all these challenges that you don't think about when you start developing a startup or developing a company. You might have a cool idea, but that's cool. That's like, I wrote this awesome code, but doesn't do anything, right? So when we were developing, we had this product. We had no clients, no farm, don't know anyone in agriculture. So even if we had a working thing, how are we going to convince farmers that we're going to save them lots of money, right? Are we going to let anyone put like a random? I think someone's sound is on. Jonathan, if you want to mute. Anyway, we can figure it out. So these are all the kind of issues that we were dealing with or not dealing with at the time when I first started working there. Because at the time we were being all engineering about it and being like, hey, let's build a cool thing. And so this is kind of like the original concept. So if you look at the middle image, this is the first draft or the first prototype of what is now in that orange box that you saw in the previous image, previous couple. The box on the right, that's standing on top of the big pole, right? That thing in the center is what is now in there, or at least a much more developed version. But like, there's lots of 3D printed parts. There's heaps of electronics. See on the left where we're developing with some breadboards and stuff. We've got stepper motors and drivers in there as well. I think we're experimenting with some lights in that particular picture as well, and stepper motors. So you can see, can you see my mouse? Yeah, okay. So here, some stepper motors as well. We've got a stepper motor moving up and down as well. And then here is we're experimenting with some lights because we're using imagery to do some of our analysis. And then here was the first iteration of our control board. So we're literally like doing microcontroller stuff to move motors up and down and then take pictures, and with a whole bunch of custom electronics. So it's very like engineering wise. And then over here on the left is the drone that we were going to use to take pictures of, analyze these farms, right? The way I got involved actually was I had a friend, James Cooper, who some of you might know, who was he's a mechanical engineering student now working at Stryker. He was doing his thesis on something to do with building drones. And basically he was helping to design and develop the drone that was going to be used for this for the BioScout system, right? Basically, because we couldn't really use a normal drone because of like the weight. Basically, we were going to have a sampler at the bottom of the drone, and we needed to do custom drone design basically because there were a whole lots of issues with like power and expense and things like that. So, and also we had some thesis student building a drone for us, and so I guess Lewis, the CEO, was like, yeah, that sounds cool. So the original way I actually got involved was, oh no, is the picture? Yeah, was to do this, right? So it's not a light turning on, but it's like the next best thing. So there's a thing that goes up and down and left and right, right? So that was literally the first thing I did at this company. And basically what this was going to be, it's controlled by a accelerometer, which you can't see, but it is in the background there. And the accelerometer was basically, that's a little nozzle. And the general concept was we were going to collect the samples for the disease detection. I probably should have said this before, but when we do disease detection, we talk about bacterial spore-based disease detection, not viruses or anything like that. So like when bacteria infects crops, they release spores, like most plants, in that kind of the way they like procreate and try and move about is by spores, and by collecting them, you can determine what type they are. I probably should have said that to start with, but that's how we do it. And so all of these botrytis, powdery mildew, those are types of like spores. Yeah. So the concept was, as the drone flew around, we needed to stabilize this little nozzle, right? So that it would stay level and have like standardize the airflow, because if it was moving around and the drone was, if it was moving around and the drone was flying in a different direction, we wouldn't get the correct airstream. It was the general principle what we were trying to do, and as the drone inevitably went up and down in the air, we needed to have a little control system to stabilize this drone, to stabilize this nozzle. And so that was the first thing I was asked to do, which kind of seems like a long time ago. Mainly because, we're going to the next section, the company pivoted very quickly after about the first year, or the first year of me working there, when we suddenly realized that, one, drones don't work. No one cares about losing lots of wheat, because wheat is very, very cheap. And if you get an area of infection, if you lose like a hectare, that's nothing at all in terms of that particular crop. But if you lose a hectare of avocados, that's like millions and millions and millions of dollars, which is why bread is cheap and avocados are expensive, basically. And us as engineers, we were just like, we see problem, find solution. Problem, we knew rust infection for wheat and things like that. Let's go solve that. But from a market perspective, from a business perspective, from a startup perspective, it's actually not the smartest thing to do, because that's not where the money is, right? And that's not a financially like good decision. So after about a year, we pivoted to doing what we do now, which is the boxes swiveling. And the reason we pivoted is because we were involved in Incubate and then StartMate. So I talked about Y Combinator before, which is the world's biggest accelerator program. Incubate and StartMate are two accelerator programs in Sydney, in Australia. Incubate is the University of Sydney accelerator program. I've got some stats on that as well, if I bring them up. It's the accelerator program at the University of Sydney. It's actually at the top of Wentworth, above Herman's. If you go all the way up the stairs, they have some super sweet offices. And StartMate is Australia's biggest accelerator program. It's run by a venture capitalist firm called Blackbird Ventures, which is actually funded by Atlassian. And basically these things exist in order to give money to startups to then try and make money from the startups. That's how this kind of world of investment goes a little bit. But the way these things, and the way they try and do that is by educating you as to how to run a company, right? Because without, as I've kind of mentioned throughout this, there's lots of things that as engineers and as non-business people and as people who haven't run companies, there's lots of things you need to think about that you don't normally think about. The simplest example is, do we have customers and do we have clients? Are they interested, right? Have you gone out into the community and actually asked them? You might think you know what the problem is, but you're not a farmer, right? The problem actually might be slightly different than you think. And so actually, and they're the people who are going to pay you, right? Another issue potentially is, do you have any contacts in agriculture, right? Do you know anyone who actually works in agriculture? Do you know anyone who knows anyone who works in agriculture, right? Because without that, you're never going to get involved in the actual people who you're trying to sell a product to and actually try to help, right? The other thing, in particular in agri-tech, as we've discovered, it's because they're all sort of like rural like communities. There's like the way their particular sphere of operation works is they're sort of not very trustworthy. So it's very hard to like get in and get involved and get trusted by these people because they kind of think this is probably like, not stereotyping, but generalizing a little bit, but this is kind of the experience we've had is like, they kind of stay away and they're experience like, oh, another guy from the city bring his cool tech and trying to help us and not actually do anything. So you kind of have these barriers to actually succeed that have absolutely nothing to do with the product you're trying to make. Obviously then selling, right? You've got the top level thing of, I've got this thing, is it correct? Is it solving the problem I want it to? But now how do I sell it? Like, which sounds easy, but it's like, okay, even down to is this a service? Is this a subscription thing? Do people buy this outright? How does the financials of that, like how much do I sell it for? How much can I make it for? Am I gonna make, if I sell it cheaply now, but not make much money, is that gonna benefit me later? These are all things you actually have to think about when developing. I've got the, excuse me, I am engineer, what is business? I think this kind of summarized a lot for us when we were sort of working there because these were things like even just like business terms we didn't know anything about. People, you go to a meeting and they'd say things and Lewis would come back and be like, I had to Google what these things meant in a meeting. And he's literally like the CEO of a company, right? In Evo, this is 4 of you, but it's still like, these are the kind of things you're facing. And of course, making it harder, you've got the issues of research and development while trying to do all of this stuff. So imagine you going off to 4 different meetings with customers, clients, contacts, trying to learn how to sell, trying to plan your finances for the year, and you're also trying to debug C code. Like that's the kind of thing that you're dealing with. So how do these programs actually work? Like, what are they? I've just said a bunch of stuff about problems. How does Incubate and StartMate try and help? Well, basically, to start with, what these companies do is they invest money in you. So Incubate is very, very small. It invests $5,000 across 13 weeks. So they're basically like 10 or 13, I don't remember. I think it's 10 week, like intensive programs. Imagine like a boot camp, like a company boot camp, where you start, you're given mentors. So these mentors are previous CEOs or C-levels of people who were at Incubate and got through the program and are now still in startup phase, but they're working. So they've been somewhat successful, and they come back and they try and help the people they help you go through because they've been through all the issues that you faced, and now they're trying to educate you and make you come through the other side, right? Incubate has really good contacts with Cicada, which is this other deep tech startup space over in Sydney Tech Park. They obviously have great contacts with the university, and they have great contacts with seed rounds, investors, VCs, that kind of thing. StartMate, which as I said is part of Blackwood Ventures, they're much more difficult to get into because they're Australia-wide and they're super, super competitive. They give a $75,000 investment at 7.5% equity, which basically means that they buy when they invest 75K, that buys them 7.5% of the company, right? Which basically is a $1 million valuation, right? Which is not nothing, but 75,000 disappears in like 2 weeks. It goes. It's kind of nothing. But the fact that they take equity is how they try and make money. Because if you make that $40 million valuation after 2 years, they own 7.5% of that $40 million, right? And if they have 20 successful companies, you're starting to look at a decent portion of money in that sense. And this is kind of the way these things function. I was just going to show you some videos about these kind of 10-week programs are sort of like a semester. They're like 10 weeks, except you have one subject, and that subject is like Tron 3. And you're also trying to sell your product, talk to people who are trying to buy your product, and develop it at the same time. That's why it's pretty crazy. So this video on the left was us at the beginning when we hadn't pivoted yet, and we were doing drone tests. Well, it's a great video to show you things don't always work out. That's the wrong video. I want to show this one. So we were out at some farm doing tests, and we basically were trying to check. So I'll just pause it. There's the drone, and the thing underneath it is like the sampler. So basically it's meant to fly through and collect samples, right? It didn't, well, let it play. We're waiting for success. Oh, this was after like 5 weeks of kind of like development. And then we finally went out to the farm. We were like, yeah, we're going to get some awesome test results. And then everything broke. It rained. It was crap, right? It's like, these weeks are intense. And after it was like 3 days after this, we decided to stop using drones as well. The video on the right is the last week of demo day and the last week before demo day. And basically what we were trying to do was we finally got some clients, we finally got some people who were potentially interested in doing a field trial. And we had to like get them up to some farm in like northern New South Wales on the Monday. Now we didn't have a product finished to like, they wanted a box. They wanted the thing that you saw on the sticks earlier in the video. It didn't exist yet. So this was at 3 a.m. on Sunday night. So these are the boxes unbuilt. This is us still developing electronics and doing testing. Hopefully everyone can see the video. And then I don't know if you can see, but where my mouse is, these are 4 of the products that we were trying to send up, still not in their cases yet, and the electronics still hadn't been tested yet. So this was 3 a.m., like at 10 hours before we had to send them up to Queensland. That's also in our co-founder's like mum's house, which it doesn't say like startup vibes to you, I don't know what will. So like, that was the kind of like stuff we didn't sleep the whole weekend. So that was the kind of stuff that you kind of tend to go through when you're got like a 13-week intensive period. And at the end of the day, you're trying to develop a product and sell it. Because that's what you're trying to do. So at the end of this 13-week period, we have a pitch day, exactly like you see in Silicon Valley, which is really cool. So this was down at, I think it was at the ICC. Or it wasn't the ICC, it hadn't been built yet. It was down on the harbor, and Incubate rented out the whole space. And you basically go up and do the cliche, like you do the pitches. And it's like a really awesome kind of experience where you get to show off the stuff you've been working on for the last 13 weeks. And all of these people that come are investors. So you have like the R&D offices from Telstra there. You have all the different VCs. You have banks coming in. Like every single big company in Australia that talks about investing, this is where they come to. And this is like a university, this is the university accelerator start. So this was at the Incubate. I don't have photos from StartMate. But this is kind of the way these things function, where you do your demo day and then people come along and look and see if they're interested in potentially giving you money. So you really need to do, it's kind of in the same way that no one looks no one looks at the code that you write for a major project. It's all summarized in those 5 pages of the 40-page report that they might read. And if you can get across in those 5 pages what you're trying to do, then maybe you'll do a good job. So this is a photo of the start of the Incubate guys from the year when we did it. And they make us like all awkwardly pose. And it's kind of like, you're like, oh, wow, this is a bit cliche. So this is Lewis, the CEO of BioScout. This guy is, I don't remember his name off the top of my head, but he developed VisoSpace, which is a really cool startup doing like virtual reality, like add-ons and stuff. So they were doing like these like floating hoverboard kind of things for virtual reality, and then haptic feedback gloves as well. These 2 guys, I want to point out, they're working at, they started a company called Green Alice, which is basically doing, it's like a robotics mechatronics core, a bit like us, like a super techie startup. And they're basically doing automation of like when fruit is like ripe, which is actually a really hard problem because like manually you miss out on apples and bananas and stuff like that if you visually do it. But they have these robots that like drive down the orchards and stuff and detect which ones are ripe and stuff, and it saves them heaps of money. The other reason I point them out is because they're basically like the Tron gurus. They're at ACFR before they went to this company. The guy on the left, Steve, wrote Tron 2 back like, I don't know, 10 years ago, 30 years ago, whenever it was written. But yeah, so I just want to point that out because they're kind of see the progression of guys doing mechatronics and then the startups and things like that as well. Okay, timing is actually going okay because I didn't have too much on this section, but briefly, what did I actually do is cool. I talked about a bunch of random stuff and how the economy sort of developed. So what did I do? How did I not break everything? So the first year I was there was mostly like kind of your core electrical and mechatronic stuff. I've just broken these down just by general themes of what I actually did kind of across those 3 years. And it sort of has broken down actually pretty nicely when I started thinking about. So mostly the electronics and mechatronic stuff. So when I first got there, as you saw in those early photos in biomed labs, we were developing like the hardware. So there's lots of sensors that are in there. We have things that need to move because we need to take pictures of things. We need to analyze some data visually. We need to analyze some data from like sensor collector data. And then we have like heat and temperature sensors and things like that. We have fans we need to actuate. We have lights we need to turn on off. And all of this needs to be done with electronics. And so we were, doing PCB design. We were like looking around with Arduinos, and we had different voltages of regulation we needed to do. So it was very mechatronics kind of esque thing before we really even got to the kind of more software section. Kind of second year, I was there, started to be more, we moved off that a little bit. And so we had the core electronics down. We started working on the actual core CPU architecture, not the like electronic architecture, but like the software architecture on the CPU that would actually do all this stuff. Because if you think about, I'll get to the more detailed stuff in a second, as well as doing some image analysis, actually quite a lot of image analysis. The third year, which was sort of like being the last year, was doing a lot of system architecture design for like reliability, robustness. We were also starting to do the electronics, and the general software pipeline was good. And so we needed to start it's like we'd like done the major project. It was like done. We had a product, Una product, right? But now we have 20 in 20 different fields in random farms across Australia, right? So suddenly you need to have to scale it. You have to be able to control all of them. Some of them have different hardware. Some of them we're doing testing on. And how do you manage all of that when people in the company leave or come back, or when you have to do something else? You can't have kind of nitty-gritty code or a nitty-gritty pipeline that doesn't work and doesn't work for every single variant of the thing you're trying to deal with. And sometimes it's not even like in the state, right? So if like something fails, like properly fails, or you don't have a good pipeline, you have to fly to like Queensland, get on a truck, drive 6 hours, and then be like, oh, there's a loose wire or something, right? Or like, oh, we could have fixed that in software or something like that, right? So that's the whole kind of whole scalability aspect coming into it, which is, hey, I have a product, how does it work? Or how do I make it work? So this is, the general principle. So we sample in the air, we detect it, automated microscopy, machine learning, machine vision and learning, which basically is a fancy way of saying we take photos of spores, right? And then we pass them through the most basic classifier in the world. It's the general principle of how it works. It's a little bit more complicated than that. And the taking pictures of spores is a really difficult problem. And when I said the image analysis stuff back here, that's what I spent a good portion of my time doing. Because these are very, 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 very small, 5 to 30 nano micrometers, mu meters. These are very, very, very small things. And to take good photos, good enough for classification, is a very difficult problem. One that we still haven't quite solved yet as well. There's a lot of issues around trying to get that good. And then once we analyze it, we suddenly have spore density, so the amount of spores that we've detected at a certain time, at a certain place. And so suddenly you have all this information that is suddenly useful to the farmer, because you know that on this day at some time we had a high density of spores, and then the next day the farm south, or the monitor south of that, started getting the same spores. And so suddenly you can start tracking the movement of these spores and if there are more or less or things like that, right? So this is the block diagram of the image we saw earlier, which is actually what it, like how it functions. It's super nice, clean pipeline. It's very easy to explain to someone. You have data, you collect it in the field, you analyze it, goes to your front end, and then the client uses it. Which of course is not at all actually what it looks like. So if we just take this hardware block, because I didn't do a block diagram for the other ones, if we just take this hardware block, this is kind of what it looks like, right? From an actual software, like development point of view, I guess. Can I zoom in because it's pretty intense. So we've got all of these different components that are literally, we're managing bits of hardware and trying to, like, the question at these big product, like projects and stuff is like, if I have 10 different sensors, how am I going to get all of that data? How am I going to deal with it? What happens if the system shuts down, right? How do I know what I was doing before? If I'm currently running something, how do I stop that? How do I remember where I was before? What happens if a sensor fails? Does it send data? Does it not send data? Do I, like, these are kind of all questions you need to think about, and that they're suddenly not like, oh, I guess we won't get good marks. It's suddenly like, okay, if this, if this thing breaks or we suddenly stop getting data, like, what do we do? Right? Like, do we tell the farmer to go turn it on and off again? Like, these are kind of all like questions that are specific to like having a company or having a product, as opposed to developing something just for like an assignment, or developing like a bit of engineering thing like, oh, it's fine, or like it works 8 times out of 10. Or like if I want to, and the other thing as well is like the, when you're kind of building something like this, you have to start thinking about, and these are all sort of things I've learned. Like, I didn't know this when I first started doing it. This is like a diagram from maybe like a year and a half ago. It looks very different now. But you kind of have to think like, you know, it's not like your assignment is done and you don't have to touch it again. It's like this thing gets developed and touched by lots and lots of people. So how does the code need to be written and developed so that we can extend it or change it, or other people can actually use it? If you've got 4 people working on different sections, how are we going to bring it all together? And it's in a much more complicated testing fashion than if you're just working like locally, because these things are off in fields and things like that. So a very brief overview of the actual things I was dealing with, the actual electronics. So we have different environment sensors. So you can see, I think we've got GPS, MOX, which is like CO2 and like air quality. We've got, it says BMP, it's actually a BME sensor, which is like humidity and temperature and things like that. We've got the NOVA sensor, which is like ppm measurements, so like how many parts per million in the air and things like that. And we also have an anemometer, which is like wind speed and things like that. So these are all like the kind of environment sensors. Location sensor, GPS. We have a bunch of actuators. These are all these are all stuff you deal with in like Tron 2 and Tron 3. Like, it's the code and the way this is developed is no different from that sort of architecture. So when I was writing it, we took that. It's like, so this is also for all the Tron people here. This is also all written in C on a microcontroller. Like, it's very same kind of thing that you would all be familiar with. So it's not like steps and steps above. Reset systems, that's all like custom electronics and power control systems where we want to be able to like, so I said before, like, how do you get the farmer to turn, like, you can't tell the farmer to go and turn an off switch. You can if you code it in and develop one. So we have like a hard off switch, which we push a button and it turns off the power to our CPU, and then it turns it back on again. So we can do hard resets and things like that. But that's all custom. We have different PID controllers for like fan control and things like that, as well as dealing with 4G, as we're in the middle of rural Queensland. So these are all like systems that developed individually are fine, but bringing them together can be quite challenging. I think it's the last slide, yeah. So the last thing on actual software systems that maybe differ to the way we develop them at uni is we've got real-time sensor capacities that we need to start to think about that are not on microcontrollers. So what kind of architecture are we looking for that? As I mentioned before, like failure modes, you can't just pick up the thing and turn it off and turn it on again, right? Or hit a reset switch or recompile the code or something like that. So what these things need to operate hundreds of thousands of kilometers away by themselves. Like, you can't monitor it all the time. So how are you going to integrate that into your system? How are we monitoring the state of our system, right? If there's 10 different components and couple of different boards, right? Two different microcontrollers, Raspberry Pis, etc. How are we dealing with all the information going between them? Do they act independently? Do they act together? What's the best for our failure system? Right? Again, questions when you're dealing with more complicated systems that you don't necessarily need to think about the rest of the time. The last thing, one of the last things I was working was automated deployment. So we've got a bunch of different devices with different hardware, things like that, which require like different drivers and things like that. So how do you modify code, or how do you modify a system scalably for things that are different? Like, it's not like you have one robot and then you give them all code, right? Like, it's a bit like, to do it in a fashion that is scalable is not like an easy thing, and there's no off-the-shelf solution for these sorts of things. There's nothing where you can be like, okay, I'm going to download, like, this guy's written this bit of code. It doesn't, the kind of the technology and the commercialization hasn't gone far enough for a lot of these things. So a lot of these things, some of the time we're deciding off the shelf between off the shelf components and custom, which is potentially a matter of you're weighing up time versus design. But some of the times you don't have a choice. Some of the times you have to figure out the best way of doing something, but you don't have a gold standard to do it. Same thing with testing. How do you test these devices? And it's suddenly not a matter of passing unit tests for getting on ed. It's a matter of like, okay, if I change this, is my system in Queensland going to break? Right? So something becomes much more important. And the same with communication. If I don't get communication, is my device going to be okay? Last thing, practical in an hour. One of the kind of key thing, I already talked about custom hardware versus off the shelf, but kind of the key things I noticed working at software hard ops is that there's a big difference between good code and working code. Good code is code that is scalable and designed well, or just good systems in general. And working code is most of what we write at uni because it works, right? But then you stop working on the code and you don't ever have to touch it again. So you're not building on it, you're not extending it. And there's a big difference between the two. And also at startups, you're not like got heaps of money and heaps of time to develop something. So sometimes you really need a balance. Writing good code so you don't have to go back and change it later, but also not spending 2 weeks writing good code, because in that time you could like add to your product and add to your client and get something out to the farmer, which will then get you money and get him to buy another product, right? Whose responsibility is when it breaks? At the end of the day, it's yours. I mean, there is a demo day, it's the pitch day, but there is no demo day as in an assignment. It's all on you when it breaks, because you're the one who designs it, and there's no manager necessarily. I didn't really have a manager. Some startups obviously different, but I didn't. And so you kind of, it's a different attitude to have, because at least my experience, I was like very lucky, the people I work with, but there was no one basically being like, oh, this is crap, this is not good. It was all about like, okay, it didn't work, what can we do to fix it? Can you fix it? But it was all on me to be able to do both of those. And not everyone, it's not like kind of the environment for everyone. And those were some big kind of takeaways, being like, am I okay with if this doesn't work? Or if I don't know how to do something, am I okay with understanding that and going to try to do it the best way anyway? Because it's not like you have code reviews or anything like that you might have at a bigger company. And I had at Qantas, to be fair, and is kind of code practice. But when you're trying to get something to work in a very limited time, it's a very different attitude you have towards trying to design something. Thank you for listening. Ooh, that felt quite long. I would just feel like I'd left with this picture, which is my favorite picture that we managed to. So this is a screenshot of a bug on a microscope that has been squished somewhere in rural New South Wales. And we took a photo of it. And when the light came on, it shone through and it left us this awesome picture. So I thought I'd just leave that here. Yeah, happy to take any questions. I don't know if there's anything in the chat. Steve asked me, what would you say the portions of things you learned on the job versus learnt from uni? Definitely more learnt out on the job. I feel like learnt a lot more application skills, just like some of the things like how to deal with Raspberry Pis and some basic like networking, or like, which are things like you don't really learn at uni, but you like need in like the real world of mechatronics. So I'd probably say maybe like 70-30 to stuff I learned at BioScout. There are a lot of things that I learned at uni that I wasn't able to apply. Like a lot of the mechatronics stuff, like the core Tron 2 stuff, I learned at uni and was able to apply that. And then I've learned a lot of stuff at BioScout that I'm now able to put back into my subjects here. What was unexpected? Yeah, please speak up as well rather than just typing if you have any questions. What was an unexpected challenge or surprise you? Where was the question? Oh, what was an unexpected challenge or surprise you encountered while working at BioScout, either technically or in a business sense? An unexpected challenge. I think probably like being confident with, like maybe I think how much was left to me in terms of like design, or like getting, we kind of have an end goal, but the end goal is to get things working. It's not like we do agile development every week, this is what the goal is. It's sort of very much down, like we're just trying to get this thing working. And it was very much down to me for each week, like what the goals I was going to set and how I was going to get it done. And what occasionally those would come to me, like, we need to get this done because we have to do this, like we have to do this release or something like that. But it was very much down to me each week, like what I was going to get done. And I think that was being okay with that and getting used to managing my weeks like that were very difficult, or very different, I think. O3 is a BioScout. How do you do a financial skills change? Not much. As I said, I kind of stayed away from the financials a little bit, just in the sense that I think I just preferred being on the coding side, or just like being the engineer in the team rather than being involved in the financials. But I know, for example, our CFO who did mechanical engineering here, he is now like, actually he's not the CFO, but he's basically doing all our financial pipelines and planning for the entire company. And so he's put himself in a position where he's learned a lot about how these things work. And he kind of helps direct the rest of us in terms of our goals from a financial perspective. And I think I could have been more involved with that if I chose to be. How did COVID impact on BioScout? Actually, we were pretty lucky with COVID. One, it's a pretty small team. So for the most part, people were still kind of going into the office at least. And also to some extent, we can work remotely because a lot of our devices are remote anyway. So even in the office, yeah, we've got like devices there that we're working on, but there's a lot of like ones that in Queensland that we're working on. So it's kind of remote anyway. So that thing didn't affect us. It was also nice because we were meant to do a new release of some new devices about when COVID hit, and there was no way we were going to make that deadline. And so COVID extended it out, and we ended up getting a financial, we ended up getting a contract from the government that we wouldn't have got because we wouldn't have delivered, but because everything got pushed back like 8 months, we were able to. So it actually worked out pretty well for us. It was great. Job stability in a company such as Qantas and a startup.
I'm sorry. Like, I guess I was trying to ask, like, what do you think of like, well, obviously after COVID, stability in jobs is like quite important because a lot of people were made redundant. And how did you feel like, in terms of like job stability in a startup? Because, you know, obviously it could be impacted due to many reasons versus like your experience working like at Qantas.
Yeah.
Like, you know.
Do you mean for me, like us specifically, or like startups in general, do I think?
Like startups in general, I guess. Yeah.
I think in general, tech startups seem to do okay. Mainly because there wasn't that much of an impact, relatively speaking, on tech. A lot of things could be remote anyway, because like you can do a software job from home. And the tech industry in general wasn't affected so much, I think. Like people weren't like losing, yeah, at least in startups, like there were like layoffs obviously in like big companies. Like Qantas had well, Qantas is the airline industry, so obviously that's a bad example. But like I was working at another startup during COVID, like at the end, like June, July last year, and we were over at the startup space at UNSW, and they were like everyone was kind of doing fine, because the money's kept like on rolling, and people still wanted to invest. I think is the other thing. Even though they were losing money, like everyone was still open to supporting the startups because they needed them, at least afterwards. So I think it was okay. I'm sure someone else who actually, I'm sure like a VC would disagree with me, but it felt okay. Yeah. Any other questions?